Hello class, today we're on lesson number 2 in chapter 10 on page 450 of our textbook. Okay, and we have up here at the top a cartoon, and the one person asks, think of a number from 1 to 1,000. So his number is 684. And then he says, that's right. How do you do that? Well, he was obviously right. There was a number, but there's a really neat number trick here that we're going to go over. It says, here's a number trick that is somewhat more impressive than the one in this cartoon. Think of a 3-digit number and write it down twice to form a 6-digit number. Regardless of what number is originally chosen, the resulting 6-digit number can be divided evenly by 7, 11, and 13. For example, beginning with the number of this cartoon, 684, we get 684,684. The results of dividing 684,684 by 7, 11, and 13 are shown here, and we can see that they evenly divide. 7 goes into it 97,812 times, and we see 11, and we see 13, and they all evenly divide. Now, most numbers, at the top of page 451, most numbers cannot be divided evenly by even one of those numbers, let alone all three. So why is it, no matter what 3-digit number that you begin with, the 6-digit number form can be divided evenly by those three numbers? Now the reason has to do with the way that the 6-digit number is produced. Writing down a 3-digit number twice is equivalent to multiplying it by 1001. So if you took any number, and we can see the illustration over here to the right, take a look, and we're going to actually do it up here on our board as well. And let's see. So we have, sorry, my board. Okay, so we have 684, and we're going to multiply this by 1001. So what's going to happen? Well, if you follow, you know you're going to have 684 here because you're multiplying it by 1. Okay? Then this will be 0. Obviously 0, you put all three zeros because you're going to multiply all three, 684, all three digits, and then you're going to have another set of zeros. And then you're going to have another 1. Okay? And what's going to happen is that you're going to get 684. You'll have 4, and you'll have 8, and you'll have 6, right? Because you're just multiplying this by 1, and you're multiplying this by 1. And that's what gives us this number, 684,684. And again, if you took any 3-digit number, it would do the same, because you would be multiplying any 3-digit number up here by 1, so you'll have that 3-digit number here. And then you'll have 2 zeros, which would create these zeros here, and then you'd have that same 3-digit number being multiplied again. So if we take this and start looking at the factors of this 3-digit number, this little trick that we're working with, and we're saying take a 3-digit number and then repeat it and say, well, make a 6-digit number out of it. This is what we're doing. We're always multiplying by 1001 in effect, okay? Though we're not actually doing it, but that's what we're doing, and we're saying to add the same 3 digits to either the front or the end, whichever way, but you're creating that 6-digit number. Now let's continue reading on here. It says writing down a 3-digit number twice is equivalent to multiplying it by 1001. The number 1001 is composite, being the product, get this, of 7, 11, and 13. Okay? If we let x represent the 3-digit number first chosen, then 1001x represents the 6-digit number form. So, as I was saying, we have this number in parentheses. Let's picture that simply being as 1000, okay, 1, and I can put a little comma here. They're using their commas. We should. 1001x, okay? Because x will be this number up here. In this case, it was 684. Now, we know that we can divide 1001, we can divide that evenly by 7, 11, and 13. Now, because 1001 is the product of 7, 11, and 13, take your calculators and just multiply 7 times 11 times 13. You'll see it's 1001. Okay. We can say that this is equal to, we're going to pull out the factors here, 7 times 11 times 13x. Okay, we have now, and I should put times here as well. Okay, we have a little time. So we're showing 4 different factors here. We're multiplying 7 times 11 times 13 times x, and we know x is going to be that 3-digit number, let's say. So no matter what number x represents, 7 times 11 times 13 times x can be evenly divided by 7, 11, and 13. Okay, so that's really the reason why this trick works. It's not so much a trick, it's just another way of representing that 1001 by telling someone, give me a 3-digit number, now repeat the 3-digit number to form a 6-digit number. Again, that was the little secret. That was the trick in there, because by doing that, we're actually saying multiply it by 7, by 11, and by 13. Okay, now I don't know how astounding it is for you to say, wow, a number, such a big number is always going to be divided by 7, 11, and 13. But as they stated, most numbers can't even be divided by one of these, okay, let alone all 3. But again, we use this we use this method just to show you how we broke them down into factors and why this is so. Now, the numbers 7, 11, and 13 are factors of the monomial 1001x because they are factors of its coefficient. Okay, we know the coefficient is 1001, and those are the factors, 7, 11, and 13. Okay, now we can take a look down here. It says 1. The other factors are 1 and 1001. We can multiply 77 because 7 times 11 is equal to 77, 91 because 7 times 13 is 91, and 143 because 11 times 13 is 143. So, you know, we can multiply any of these, and we could have said, okay, let's multiply 7 times 11, and we got 77. So we have 77 times 13, right? Because we multiply these two. We could do that easily. What else could we do? Well, we could, as they stated, 11 times 13. So we could say 7 times 11 times 13, which is 143, times x. Okay, so this coefficient, all the factors, we can sit down and try to figure out all these factors, is to be able to recognize factors of monomial expressions is a skill needed in solving many algebra problems. Repeat. To be able to recognize factors of monomial expressions is a skill needed in solving many algebra problems. Now, part of it is understanding the variable and understanding how we deal with exponents, and that we learned in the previous chapter. But and in dealing with exponents, we already learned the different laws of exponents, so we'll be able to apply those laws to the variables. Typically, that's what our challenge is when we're dealing with the exponent side. So when we have x squared, x cubed, and being able to understand how to handle polynomials and understanding what like terms are and what you can combine, but it does, a lot of this does come back towards the coefficient and being able to recognize the factors of the coefficient. So that's going to be a little bit of a challenge if we're not as well versed in multiplication. Then it's going to be more of a challenge, and it's going to force you to think a little more. I'm probably going to be more concerned about you being able to handle the exponents within these expressions and be able to factor them out and recognize those opportunities. So, but yeah, part of this is going to be with the coefficient itself. So let's take a look at the example we have here. What are the factors of 6 and x squared, or 6x squared rather, I should have said. And let's go here and let's represent that. We have 6x squared. In fact, let me clean up my board a little here, just so we can have a little room. We have a couple examples here. And we have 6x squared. And so we have to think in terms of both the coefficient and the actual variable. So we know that we can multiply 6 as 2 times 3. Okay. And we know that we can factor out x times x. So we have 2 times 3 times x times x, okay? And so 3 of its factors are 2, 3, and x, okay? These are different factors. We have 2, we have 3, and we have x, okay? Now you say, well, there's another x. Well, we've already identified x as a factor. But are there others? Well, we know that 1 and 6 are factors, right? So we can put 1 and 6 down as factors. And we can also look at the other the varying factors when we multiply. We can multiply x times 2, so 2x would be a factor, right? We can also multiply. Well, actually, let's go back to x squared. X squared is a factor. That should be up here. Sorry about that. So we multiply 1 times 6 times x squared. Now, of course, when we're breaking this down into its simplest factors, we're going to have x times x, but x squared is a factor. But then we have 2x. Now we can also multiply the 2 times the x squared, and that would be 2x squared, right? That would be a factor. Well, we multiply 2x squared by 3. That would be 6x squared. Another factor would be 3 times x, so that would be 3x. And of course, then 3x squared would be another factor. And that you would multiply by 2 to get 6x squared. The 3x you would multiply by 2x, or 2 and x. And then lastly, we know that 6x is a factor, and so is 6x squared, which of course you just multiply by 1 to get 6x squared. So we can see there are many factors here. In fact, we can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 different factors. And again, we're just using whole numbers here. We're using integers, let's say, and by using integers, we're really just limiting. We can use decimals and fractions, obviously, and this could there's just an infinite number. So we're certainly challenged to determine all of these factors. And you have to really think thoroughly, very thorough in your thinking. Now, in general, the factors of monomial ax to the nth power include the factors of the coefficient a, the factors of the x to the nth power, that would be x, x squared, x to the nth power, and the products of various combinations of these factors. And that's what we did over here. So we had the 2 and the 3, obviously the 1 and the 6, but then we were able to come up with a whole bunch of different factors by simply multiplying them all together in different ways. And to be thorough, you know, you may run into a particular problem, and you may be able to determine this is the factor I need. So you're not always going to have to know every single factor, but you'll be able to see that common factor, and that's what's going to be helpful, particularly when we're factoring out different expressions. Okay. Now, in lesson 1, we defined the greatest common factor of the set of numbers to be the largest integer that is a factor of all the numbers, and said that the two numbers whose greatest common factor is 1 are relatively prime. We will now apply these ideas to monomials with integer coefficients. Now, turn over to page 452. And we see here, consider, for example, the monomials 4x to the 5th power and 6x to the 3rd power. The greatest common factor of their coefficients is 2. Okay, so we have, let's make some more room over here. Get my eraser, big eraser. Look at this, just erase the entire board. How's that? Okay. Now, we're talking about the greatest common factor, and the first thing we're looking at is the coefficient, and that coefficient of each is 4 and 6. All right, so simple number. We have 4 and we have 6. And we know that this is 2 times 2, and this is 2 times 3. Okay, so we know 2 to be the greatest common factor of their coefficients. Now we also have x to the 5th power, and then we have x to the 3rd power. Now what would be the greatest common factor of the monomial? All right, that would be the highest. That would be the highest power of x, because we can multiply. Well, let's just go ahead and say that it would be x to the 3rd. Why? Well, we have x to the 3rd because we can multiply that times 1, and that would obviously be a factor here. But over here, we know that we would have x to the 3rd times x squared. We would add these two. That would be x to the 5th, right? So we know that x to the 3rd is our greatest common factor with the variable, and so we would say that 2x to the 3rd power, that would be the greatest common factor. Okay, so the greatest common factor of a set of monomials with integer coefficients is the product of the greatest common factor of their coefficients and the highest power of each variable that is a factor of all the monomials. And quite simply, anytime you see something with a variable, let's say you have x to the 10th power and then you have x to the 7th power, it's very, very easy. We always go with the number here, the lower one, because we know we can express this as x to the 7th times x to the 3rd. So x to the 7th would be the greatest common factor of the variable. Okay, so if you have two numbers, you take the exponent that's the lowest. If I had 3 different ones, again, we're just pausing here, just showing, let's add x to the 7th power, and let's add x to the 5th power, and then I have x squared. What's the greatest common factor? It's always going to be the smallest one, x squared. Why? Well, this is x squared times 1. This is x squared times x to the 3rd, and this is x squared times x to the 5th. Okay, we're always adding. Okay, I'm doing them quickly because I know I need to add them to get to the exponent, right? So x squared, and x squared. That's the greatest common factor. The greatest common factor will always be the lowest in a sense when we're using the same variable, okay, because it gets a little, you'll have other elements to this and they're going to make it more complex with multiple variables, okay, but when we're looking at just that one single variable, just go to the lowest exponent and that will be your greatest common factor. As you can see, it worked over here. X to the 3rd was our lowest power or exponent, and we basically use that over here. So now let's go back and look at the our book. It says here again, the greatest common factor of a set of monomials with integer coefficients is the product of the greatest common factor of their coefficients and the highest power of each variable that is a factor of all the monomials. Now that's a very general statement because it's going to become more complex. I showed you a simple shortcut just looking at one single variable, but we're going to make it a little bit tougher on you because we're going to really force you to think. Now, like two numbers, two monomials whose greatest common factor is 1 are relatively prime. Okay, so let's take a look here at example number 2. I'm going to clean up my board and let's go ahead and take a look at these examples. It says find the greatest common factor of 3x cubed and 7x to the 7th power. Okay, so we can do just like what they did there, and they put 3x cubed, and that's going to be equal to 3 times x times x times x, and then we have 7x to the 7th. Okay, that's going to be a lot of 7s there, or a lot of x's. So we have 7 times x. Oh, that x is almost looks like a TP. X times x times x, and I still need 4 more. Oop, I am running out of room here on my tablet, which is causing me to draw these wrong. Okay, I think that's 7. 1, 2, 3, 4, 5, 6, 7, x to the 7th power. So, what would be the greatest common factor? Well, we don't have a coefficient that's going to have a common factor other than 1. 1 times 3 and 1 times 7. So that's not going to work. But we do see here, look, 3 x's, right? And we have 3 x's, okay? Now notice that'll give us x to the 3rd power. So that would be the greatest common factor. But remember what I said earlier. You take the monomial with the lowest power, if they're, again, the same, I say variable, not monomial, the same variable with the lowest power. Again, they have to be the same variable. Okay, if this were x and this were y, then that would be, they would not be common. But we have x to the 3rd and x to the 7th, so it's x to the 3rd power. Okay, and we can see they did the same here on example number 3. They have 6 times xy, and they broke that down into 2 times 3 times x times y, and then we have 15 y to the 4th. So we had 3 times 5 times y times y times y. And now we're looking for those common factors. In fact, I think I had better put this on the board just so I can really focus on how they're picking these out. So we have 6, x, and y. And that y looks like an x. So we have 2 times 3 times x times y. And then we had 15. Right, these very large. 15. Oh, I'm sorry, there's no x. There's a y to the 4th. Okay, so what would that look like? Well, that would be 3 times 5 times y times y times y times y. Okay, so we're looking for those common. So we would have to take all of the common factors, okay, and we have a 3. The 2 is not common. The 3 is. The x is not common. The y is common. Okay, we have at least one y. So we would just take those factors and we can say that 3y is a common factor because we have to pull those factors out. These are the common. We can multiply them together and say that 3y is the greatest common factor because we're multiplying them together. Okay. Now we have 9 squared and 4y squared. Now let's just take a look what happened here. 9x squared is 3 times 3 times x, and then we have 4y squared, which is 2 times y. Now look at what we have. We don't have anything that's common. Okay, the only factor of these monomials that they have in common is 1, so they are relatively prime. Okay, so here's just a great lesson to teach us how to break apart monomials. Very important that we can break apart the monomials, because once we break those apart, we're going to be able to identify those common factors. And it's going to be very, very important, as they stated. I'll go back to page 451. To be able to recognize factors of monomial expressions is a skill needed in solving many algebra problems. So focus on doing this. And hopefully you're not going to be so challenged with your multiplication table. Again, I'm more concerned particularly about how you handle those variables. Okay, that's where you're going to be challenged to apply the knowledge that you've learned in this particular class.